And we're back, ready to continue with Calculus 2, moving on to section 11.2. So in 11.1 we introduced sequences, and in 11.2 we're introducing series, and this will be the primary topic for the rest of chapter 11, is dealing with series. So the first thing is to define what is a series. A series looks like this. So if you recall the capital sigma notation, that's summation notation. So what we're doing is we're adding up terms from a sequence. So we have a sequence AN, we're adding up all those terms from n equals whatever the starting n value is. It may not be 1 all the time, but n equals 1, but then going on to n equals infinity. In other words, we add up all the terms of the sequence forever. So these are infinite sums. Right, so just to write it out. So whatever n starts with, n equals 1, we'd plug in that n value to get a1. And then the sigma means we're adding up, so plus, then we work our way up, a2 plus a3 plus a4, and so on. Ordinarily, when we deal with sigma notation, there's a starting point and an ending point, and you'd stop when you get to the number at the top. But when this is a series, it doesn't stop. It goes on forever. Okay, so that's what it means. Let's talk about what the actual calculation is. Okay. So in general, I can't just say I'm going to add up these infinitely many numbers and get an answer out of that, get a number. All right. So the kth partial sum of the series is, we call it S sub k. And what it is it's the sum, it looks the same, summation of an, where n starts with whatever this is, same number, n starts with 1, but now we stop when we get to the k. So it's no longer an infinite sum, it's a finite sum. So this is a1 plus a2, and so on until we get to plus ak. Now, there's no question at all that if I have a sequence, I can add up the first k terms, I can add up the first k numbers in that sequence, and I will get an answer. I will get a finite answer out of this. Okay, so to figure out the limit of this, figure out the value of the series, we would need to take the limit of these partial sums as k approaches infinity. So I'll write that down next. Okay, so for a series, for a given series, that was a comma, but I don't want to confuse. For a given series, we have a sequence of partial sums now. And if the limit as k approaches infinity of sk, you look at the limit of that sequence of partial sums, if that equals a number L, and this is finite, then we say the series has value L. this infinite sum, we say equals L. Another bit of terminology is when this happens, the series is convergent. All right. On the other hand, I guess I have to erase. On the other hand, if this limit doesn't exist, so we always have this sequence of partial sums. If the limit exists, meaning it's a finite answer, then we say the series is convergent and its value is equal to this same L here. But if, let me just erase this last part. If the limit of the series, if the limit of the sequence of partial sums does not exist, and that includes it equaling infinity, then we say the series is divergent. All right, so let's look at a specific example and figure it out from scratch. So I want to look at the series summation of, we'll say 1 over 2 to the n minus 1 power, where n starts at 1 and goes to infinity. All right, so we want to answer two questions. The first question is this series convergent or divergent? If it's divergent, that's all we have to say. The series is divergent. If it's convergent, then there's another question, a follow-up question. What is its value? All right, but to answer both of them, or either of them, both questions, at this point we have to look at the partial sums. So SK for this series, SK is the sum I get starting with n equals 1 and ending with n equals k. So let's just write it out here. When n is 1, I get 1/2 to the, I'll simplify this after I write it the first time. 1/2 to the 1 minus 1 plus 1/2 to the 2 minus 1, and so on. Let me put one more actually before I skip. Plus 1/2 to the 3 minus 1, and so on until we get to 1/2 to the k minus 1. Right, so that's what the partial sum looks like. I'm going to just simplify this a little bit without rewriting it, so you may want to recopy it on a second line in your notes. I'm just going to simplify the exponents here. We'll have 0, 1, 2, 3, or 1, 2, k minus 1 I have to leave like that. Okay, I don't want to simplify my terms though. I'm trying to figure out a pattern so I can figure out a formula for SK. But what we notice, and you may have seen this before in college algebra or equivalent place, but what you notice about this particular sequence that we're adding, it's a geometric sequence. So if you look from term to term, each term is just the previous term but times another 1/2. So this is 1/2 to the 0, this is 1/2 to the 1, this is 1/2 squared, and so on. Each consecutive term, we're just multiplying by another 1/2. So what I'm going to do is I'm going to rewrite the exact same thing, except I want to write 1/2 SK. I want to multiply this whole sum by 1/2. So what that does is when I multiply each of these terms by 1/2, I'm increasing the exponent on each term by 1. And so let's write it out. Let me give myself a little bit more room there at the end. So I'm multiplying it all by 1/2. What that does is it increases the exponent each term by 1/2. So when I write it out, let me line up the terms according to their exponent. So 1/2 to the 0 when I multiply by 1/2 becomes 1/2 to the 1. 1/2 to the 1 when I multiply by 1/2 becomes 1/2 squared. And so on. But at the end, I'm going to end up with one extra column. So 1/2 to the previous one will give me 1/2 to the k minus 1. But then 1/2 times 1/2 to the k minus 1 becomes 1/2 to the k. All right. So then I've got these two lines, and I've lined up these columns so that when there's a column, the two terms in the two rows are the same. What I'm going to do is subtract this row minus this row. So if I subtract, sk minus 1/2 sk will be, let me just write it. Sk minus 1/2 sk. I'll be able to simplify that. But then the point is almost everything cancels here. Except in the first column, I just get 1/2 to the 0, which I'll simplify in the next step. And the last column, I get 0 minus 1/2 to the k. Okay, so let's clean this up a little bit. Here, I can factor out I can factor out sk. That leaves me with 1 minus 1/2 times sk equals 1 minus 1/2 to the k. So 1 minus 1/2 is 1/2. And so we can divide by 1/2 or multiply by 2 to get a formula for sk. Sk will equal 1 minus 1/2 to the k divided by 1/2. Right? So this was all work to get us to this formula. Here is our formula. I can simplify a little bit more in a second, but here's our formula for the partial sum sk. So let me rewrite that so I can do the next step. Sk equals, well, if I divide by 1/2, that's the same as multiplying by 2 on top. So this is 2 times 1 minus 1/2 to the k. So I just simplify that one more step. So now to answer the question about our series, I need to take the limit of this as k approaches infinity. Well, my function, or my sequence, the only place k appears is up here in this exponent. So if you think back to our examples from sequences, this part here, that's 1/2 to the kth power. When k grows to infinity, multiplying by 1/2 an infinite number of times, that's going to approach 0. So that piece goes to 0. That leaves me with just 2 times 1 minus 0, which is 2. Okay, so that tells us two things. The limit of the partial sums is 2, which is a finite answer. That tells us that our series is convergent, and it actually is said to equal 2. So we've answered both questions at the same time. The series is convergent, and its value is 2. Okay, so let's generalize this example. That was an example of what we call a geometric series. And so last time we talked about geometric sequences. Well, a geometric sequence can be written in some form that resembles this. A number a times r to the n, where r is some number. So that's a geometric sequence. To make it a geometric series, we're just adding it up. So let me write it like this. Summation from 0 to infinity. Now, like I said before, our series, the starting n value is frequently 1. It's also frequently 0. It can really be anything as long as it's going to infinity. That's what makes it a series. So we'll talk more generally about what makes something a geometric sequence, or what makes something a geometric series if it's not written exactly like this. But let's just go with this for the moment. Well, if I want to add this up, let's think about our trick from before. Our partial sum would look like ar to the 0 plus ar to the 1 plus ar to the 2, and so on, up to ar to the k. Then in a geometric sequence, each term, they're all the same term except they differ by how many r's they have in their product. So each term is the previous term times another r. So I do the same trick where I multiply this whole thing by r. So lining up my columns again, I'll have ar to the 0 becomes ar to the first, ar to the first becomes ar squared, and so on. And then I get an extra at the end, which is ar to the k plus 1. And now if we subtract, I'm going to skip some of the steps here. If I subtract, I get 1 minus r times sk on the left side. And then again, most of my columns cancel. I'm just left with ar to the 0, which is a. R to the 0 is 1. So a. And then 0 minus this gives us minus a r to the k plus 1. All right, so then solving this for sk again, I'll rewrite this after I clean it up. But I'm going to divide both sides by 1 minus r. And so there's our formula for sk, for the partial sum sk. Okay, so now I want to think about what is the limit of this thing. Okay, so let me just recopy the formula. I'll leave it like that. Okay, so I'm going to ask, what is the limit of this? As k goes to infinity. Well, the only place that k appears in our formula here is up here in this exponent on r. And so as we talked about last time with geometric sequences, if r is a small number, the more times you multiply by r, the smaller it gets. So if r is small, this part here will approach 0. So what that means is if r, well, we did this for negative numbers as well. If r is small means if the absolute value of r is less than 1, this part goes to 0. That would leave me with a minus 0 over 1 minus r. On the other hand, if r was big, then r to a variable power is going to get larger and larger the bigger that exponent gets. So if r is large, this thing's going to go to best case scenario infinity. Other case scenarios, it just doesn't exist. It's like alternating between positive and negative numbers. So this thing goes to something that doesn't exist when r is big. So if r is bigger than 1, if the absolute value of r is bigger than 1, this just does not exist. Now I'm going to amend that. Let's think about the special cases where absolute value of r equals 1. Well, if r is positive 1, I have a problem with division by 0 here. My trick would not have worked. I couldn't have done this trick if r equaled 1. But in the case that r is 1, then let's specify here that a is not 0 in all this. I think I did that last time. A is 0, then the whole thing's not geometric anymore. It's just 0. But if r equals 1, 1 to the n is always 1, so all I'm doing is adding up a's for every n value. So a plus a infinitely many times, that's not going to be finite. That's going to be infinite. So if r is positive 1, without going to any of this trouble of figuring out the formula for sk, we can conclude that the series is divergent. If r is negative 1, then this formula is still valid. R equals negative 1 would give me an alternating sequence here between plus or minus 1. And so this will be going between 0 and 2a in that case. And so this sequence of partial sums won't converge because it's going to just be alternating between two numbers. So the punchline of all that is, if the absolute value of r is 1, then this limit does not exist. All right, so the key takeaway here is I'll just rewrite it in terms of the series. For a geometric series, we can completely determine what the answer is. So this geometric series is divergent if absolute value of r is greater than or equal to 1, and it's convergent if the absolute value of r is less than 1, and its value is what I wrote there. A divided by 1 minus r. Now, this is the formula if my geometric series is written explicitly like this. And that's an issue because a lot of times it won't look exactly like that. So if you memorize this formula, then you also have to memorize what the formula was that gave it to us. And I don't like that. So what I instead want to do is tell you how to think about this formula. So I'll rewrite it here, but I'm going to amend it. What is A in this context? So R is important. There's no getting around R. R is the common ratio of your geometric sequence. In this sequence, it's R to the n, so R is the base of that exponential part. So that's non-negotiable. You have to know about R. But A is what I get when I plug in the starting n value. When I plug in 0 for n, r to the 0 becomes 1. That's when I get A. So the way I think of it is, let me write first. It's the initial term of the sequence divided by 1 minus r. Okay, so let's do another example where we use this formula, and I'll argue for why it's more beneficial to think of it this way. All right, so let's Okay, so let's do the summation from n equals 1 to infinity of the series, or of the sequence, -3 to the n plus 1 times 1/4 to the n minus 1. So this looks way different from our typical geometric series, but I claim this is still a geometric series, so the previous formula should apply. But what I don't want to have to do is every time I recognize something as geometric, having to go back and rewrite it in the standard form that I wrote on the previous board. So what I want to do is ask two questions. What is R? Well, the giveaway here that is geometric is we have constants, we have numbers being raised to powers involving n. And it's a product of these things. So think of it like this. Every time I increase n by 1, what am I multiplying by? Well, from this factor, every time n gets bigger, I get one more -3. So I get a -3 from this factor. From this factor, since I have an n here, every time I increase n, I get another 1/4 multiplied. So I get a 1/4 from this factor. So taken together, every time I increase n, I'm multiplying by -3 times 1/4. That's -3/4. So R is -3/4. At absolute value, R is 3/4, which is less than 1. That tells me we have a convergent series. You can answer the question, is it convergent or divergent, by figuring out what is R. And then once we know it's convergent, then we have the extra question, what is its value? And that's where I have to use the formula. And so it's the initial term, so its value, the formula is the initial term divided by 1 minus R. So again, if I think of it as A divided by 1 minus R, I'd have to answer the question, what is A? And if you take it from the original formula I gave you, you have to rewrite this formula. But this way of thinking of it is, initial term, I just need to plug in my starting n value into this sequence and come up with its value. So when n is 1, I'll get -3 to the 1 plus 1 is 2, so -3 squared, times 1/4 to the 1 minus 1, which is 0. And 1 minus R, R is -3/4. So 1 minus -3/4, which I'll then have to simplify that. So we get 9 on top, 9 times 1, divided by 1 plus 3/4. 1 plus 3/4 is 7/4. I'm working backwards here. So 9 divided by 7/4. So that's going to be 36/7. So my answer here is 36/7. So a convergent geometric series, and its value is 36/7. All right. All right, so let's talk next about some laws or rules for dealing with series. and then we'll do another example on this video probably, and leave the rest of the section for the next video. So here's our laws. These are similar to a couple of our limit laws from way back in Calculus 1. So suppose we've got two series. I'm not going to write the n equals 1 to infinity every time just because it's cumbersome. We've got two series. I want to assume that they're both convergent. So we are assuming this. Then our laws, when we're dealing with convergent series, we have some laws that we can use. So one of them is the constant multiplier law. C times an, where C is a constant. If I take that series, then that constant multiplier, it can just be pulled out of the series. And my answer would be C times whatever my answer was for just the summation of the A's. And then the second law is, if I look at the series, where the sequence I'm dealing with is the sum of the two individual sequences, so an plus bn, and then I add those all together. This is very important for this one especially. If individually these two were convergent series, like we assumed up here, then I can split this up. And to figure out the answer for this, I just figure out the answers individually and add those up together to get the final answer. Okay, so let me illustrate that with geometric series, and then let me illustrate the common mistake with this second law especially. Okay, so suppose I had the series not 5, what am I doing? 2/5 to the n minus 1/8 to the n. Let's make one of them negative. Let's make it negative 1/8 to the n. And make it n minus 1 on one of them. Okay, so 2/5 to the n minus negative 1/8 to the n minus 1. All right, so the observation here is the thing we're adding up is a sum. I mean, it's really subtraction, but because of the constant multiplier rule, we can treat that as just a sum with a minus coefficient. So we have these two individual pieces. Individually, these are both geometric series. So for this one, r is 2/5 because it's 2/5 to the nth power. So that would be a convergent series if that was all we had. This one, r equals negative 1/8. Well, the absolute value is positive 1/8, which is less than 1. So by itself, this would have been a convergent series. So if I had these individually, they would both have a finite answer. They both have a convergent answer. So if I want to find the answer to this combination, I can split this up as two separate series with the same starting point. N equals 1 is our starting value. And I know how to find the answer to each of these individually because I have my formula. So in this first one, r is 2/5, so I'd have 1 minus 2/5 on the bottom, and on the top I'd have my initial term, So when n is 1 and I plug that in, I get 2/5. So 2/5 divided by 1 minus 2/5. I'll simplify that in a second. Then I have minus the answer from this one. Well, here r is negative 1/8, so on the bottom I'd have 1 plus 1/8 minus negative 8 gives us positive plus 1/8. And my initial term here, if I plug in 1, I get a 0 exponent that gives me 1 for my first term. All right, so actually let me just edit. 1 minus 2/5, that's 3/5. 1 plus 1/8 would be 9/8. So 2/5 divided by 3/5. The 5s are going to cancel and give us 2/3. 1/9/8 is 8/9. So 2/3 minus 8/9. I would need to multiply this by 3/3 to get 6/9. So 6 minus 8 is negative 2/9. So our answer to this is negative 2/9. It's a convergent series whose value is negative 2/9. Right? Okay, so let me say one more thing about this technique we used here. I can only technically split this up once I know that individually these two would be correct. Okay, so I have to know, I can write it, but then if I carry on and get that this one doesn't exist, that means this step wasn't really true, so it doesn't help me get to the final answer for the original series. So, for example, this is kind of a silly example, but let me just go with it. If I wrote this, 2 to the n minus 2 to the n. Well, in this case, obviously these two things cancel, and this is just summation of zeros. And if I just keep adding zeros, I always get 0. This would be a convergent series with value 0. But if I were to split this up, like this, again, it looks like we have two of the same thing and they're canceling, but individually these don't have answers. So 2 to the n, that's a geometric sequence, so with r greater than 1, so this is a divergent series. So this is does not exist minus does not exist. That doesn't really make sense. You can't talk about adding or subtracting things when the things don't even exist. Okay, so this is not a good example that, I mean, you probably wouldn't make the mistake of doing that. It's really going the opposite direction is where you'd probably be more likely to make the mistake. Maybe you have two unknown series that looks like there'd be some cancellation if I combine them. I'm only allowed to combine them when individually they're convergent. I already know they're convergent. Otherwise, these two things are not equal necessarily. Okay, let me stop there for this video. I'm not done with section 11.2 yet, but I want to keep the next bit together. So this first video from 11.2 is basically about geometric series and how to deal with those, but that's just one very specific, very specialized, and very easy type of series. It's a type of series for which we can answer any question. If the series is geometric, we can completely study it and know exactly what the answers are, whether or not it converges or diverges, and what its value is when it's convergent. So let me stop there and I'll continue in the next video.